So on this slide, we're going to talk about the general features of radical reactions, and then we're going to zero in on the specific reactions in the next class or two. So the first thing that always happens is that to form a radical, you saw that you needed an input of energy. The radicals were always higher in energy than the starting material, and that's generally going to be true. So to make a radical reaction happen, you need an initiator. An initiator can be something like heat or light, or it can be an actual chemical. So the examples that we'll see most often are heat, which we're going to see abbreviated as delta, light, which we see abbreviated as H nu, or some sort of chemical. And so the most common chemical is going to be peroxide. And so peroxides are going to be abbreviated as ROOR or R2O2 or something like that, where this OO bond is a particularly weak bond and is what makes it a peroxide. So here I have the three general reactions that radicals do. The first one is the radical plus a CH bond. So this is where a CH bond would actually break. And here I've chosen cyclohexane because every CH bond is identical. So it doesn't matter what CH bond you have. And it reacts with some sort of radical X. For us, this is largely going to be chlorine and bromine to form a radical and HX, which would be HCl, HBr. So let's practice the arrow pushing for this type of reaction. We will see a ton of arrow pushing this semester. Most of it will not be radical reactions, but it's still good practice. So here, what we're doing is X is interacting with one of the two electrons in the CH bond. So what we see is one electron from X and one electron from the CH bond are getting together. That's making this normal 2-electron bond. The second electron in the CH bond is going to go to the carbon. It has to go somewhere to create this radical. So that's the first reaction we'll see. We'll talk about that more. The second reaction is that we take a radical plus an alkene. Like always, in terms of the alkene, the reactive bond is going to be the second bond, the pi bond. And this is going to form a single product. The arrow pushing for this will look somewhat similar. Again, the X will want to make a bond, but instead of making it with a CH bond, it's going to make it with the CC pi bond, which is weaker than the CH bond. And then the second electron in the pi bond is going to go to the carbon. One thing I want you to notice is that when we put the X on the end of the molecule, on this carbon here, what we've done is we've formed the more stable radical, the secondary radical. If we put the X in the middle, we would form a primary radical, which would be less stable. So we form the secondary radical, not something that looks like this. The last reaction is if a radical interacts with itself, and this can happen. Not very often because radicals are often not present in huge amounts, but if this happens, we get no radicals at the end. So here, if one X radical comes in contact with another, what's going to happen is they're just going to form a 2-electron bond together. No radicals left, unlike the first two reactions. One place where this can happen is with oxygen. So if you remember your molecular orbital theory from general chemistry, something you probably don't want to remember, but you should because it's coming back next chapter, oxygen is a diradical. It's a triplet. So oxygen can react with radicals. It acts as a radical inhibitor or a radical scavenger, and what that means is that it often can stop radicals from reacting with things like DNA in your body, which is a good thing, forming, again, a 2-electron bond. So these are the general reactions we'll see. We're going to start by focusing more on the reaction of radicals with CH bonds, and then probably deal with the reactions of radicals with alkenes next class.